Alrighty, this is FRQ number 4, and before we start, probably plug in y of t and dxdt into y1 and y2. Now, please make sure that whenever you're doing this, that you know that y1, aka y of t, is your original function for y of t, and that y2 is your derivative dxdt. Okay, so don't get confused on that. All right, so for part A, it says find the position of the particle at time t is equal to 4. Now, for the y component, that's easy because you're just looking at y4. And since that is my y1, I'm just going to do y1 of 4, and then that's going to give me 1.92. So I get 1.92. Now, the x component, however, because we're given the velocity, we need to make sure that we are doing our initial condition plus whatever we start out with. So in this case, we know that at time t is equal to 2, the x-coordinate is 1. So I'm going to do 1 plus the integral from 2 to 4 of x prime of t dt. So 1 plus math 9, 2 to 4. In this case, that's going to be y2 dx. And this gives me an x-coordinate position of 1.2306. So that means that our position at time t is equal to 4 is 1.2306. 1.92. For part B, it says find the acceleration vector when the speed is first equal to 0. So, at this point, we need to probably figure out dy dt, because remember that our speed is the square root of dy dt plus dx dt squared. We already know what dx dt is. That's great. We don't know what dy dt is. Now, because we have dy dt in our problem, we probably need to define it somewhere on part B just so that we have it. And it's not that hard because it's just you taking the derivative of this, right? And then what we're going to do here is plug in and solve for 1. So then we have, let's see, math and derivative y1. Actually, no, let's not do that. Because what I've seen is that if you actually type this in, it's going to be much quicker than you doing math 8 and then y1 of x is equal to x. I'm going to go ahead and do the square root of y2 square plus y1 square, no, not y1, y3, it's y3 now, y3 square, because y3 is my derivative, square. I'm going to basically uncheck everything else, because I don't need anything else here. And then I'm going to do 1 here, because I want to see where they intersect when the speed is 1. I'm going to change my window so that, actually, no, never mind, I'm not going to change this just yet. Okay, now it says when the first time the speed is 1. So that's probably going to be between 0 and 2 for both. So now I'm going to change my window from 0 to 2 and 0 to 2. Graph this. Second, trace intersect. find my intersection. And we can see that our intersection is at 0.5146. Unfortunately, we're not done because it's talking about the acceleration vector. So now what we need to do here is find x prime of, or x double prime, of 0.5146, and then y double prime of 0.5146. Now, remember our little trick in terms of if you did not do anything with your intersection and you still have x is equal to 0.5146, remember that the 84 will read that as 0.5146. Okay, so then all you have to do here is just take the derivative of y2 and take the derivative of y3 with respect to 0.5146. So, oh great, and add. Oof. Okay, so alpha trace y2, x is equal to x. That gives us negative 0.2544. And then we're going to do the same thing where we do alpha trace. Oh, wait, before I do that, I need to do math 8. Math 8, alpha trace y3, x is equal to x. And then we get negative 0.4091. Very cool. So that equals negative 0.254, negative 0.409. Part C is asking us find all times from 0 to 10 for which the tangent line to the curve C is vertical. So what we're doing here is setting x prime of t, aka dx dt, equal to 0. So we have sine pi t minus 2 squared over 36 is equal to 0. Now, using our handy dandy calculator here, we already know that y2 is already my derivative. So I'm just going to go from 0 to 10 in this case and go from negative 1 to 1 because I want to see where I hit 0. Did I? Nope, I did not. Probably want to check that. Then graph it. Okay. So we could see that from... Okay. So from 0 to 10, I have 1 at 2, and then I have another 1 at 8. So I have 1 at 2, and then I have 1 at 8. So t is equal to 8, and t is equal to 2. Part D is asking us, does the particle ever exceed a height of 2? And we want to justify our answer. All right, so in order to do that, we are just going to take the derivative of dy dt, which is what we already have already, set that equal to 0, and that's going to give us our maximum or minimum in this case, or in this case it's actually a maximum. Oops, not that. So then I'm going to unplug and click this one right here, check this one, and then we want to see when this is 0. So we are going to see, looks like our first time. And remember that our bounds from 0 to 10, so that thing after 10 doesn't really count. Okay, so then you get 3.16149. Oops. So then we will just plug it in into the original function, which means, using our little trick, x is going to be, plot twist, 3.62149. And we already know that y1 represents my function of y, so this means that we get 1.9354. Since this is less than 2, we never exceed a height of 2, unfortunately. For part E, it says, consider the region R bounded by the curve C, find the perimeter of the region R. Now, if you look at this, region R is this lovely thing, and then we gotta add that little height right here, or length right there. So I think that length is 3, even though it does cross at 3, but I think it's just there for the LOLs. So let me check. Actually, no. Actually, yes, I do. Because I want to find the perimeter of R. Consider the region R bounded by the curve C and the x-axis. Find the perimeter of region R. Notice how it's from 0 to 10. So we're going to go from 0 to 10, and then we are going to do x prime of t square plus y prime of t square dt, and that gives us 6.8738. And then to find the average speed, we're going to do 1/10 of that. So then if we do 1/10 of this lovely thing, we'll get 0.68738. All right. I think for part E, what it's telling you is whenever it says find the perimeter of the region R, it's only asking you to find the blue part right here. All right. We'll do 5 next.